In this video tutorial, I will be performing modal dynamics with beam elements in the release 2023x of the 3D experience. This tutorial happens to be in a series that I'm doing which are addressing the transition from the Abacus CAE program to the 3D experience solver, which is also the Abacus program, but in disguise. So it's intended for people who are either new to 3D experience, in other words, basically they want to do things from scratch, or people who actually are Abacus users and would like to explore the interface and the functionalities, etc., of the same software within the Abacus, within the 3D experience platform. Now, not all the icons are going to be available. Not all the, well, obviously the interface is completely different. It's a brand new interface. And therefore it helps people who want to make that transition. Now, the other thing is that what I try to do is to find video tutorials which are already made with the Abacus CAE program and allows the viewer to go to that particular video if they want to see how the differences are within the two software, although it's the same code, but within the two software, how they alter. Now, this particular tutorial was taken by a YouTuber down here, and the link is provided, and I will basically replicate what the person is going to be has already done. So essentially, we have a cantilever beam which is tip loaded. The cross section is given there. It's a circle. It's made of steel, and Poisson ratio is given down here. And this is a dynamic problem in a sense that the load P is applied according to this time history uh, pattern. Now, the problem being linear, it can be very efficiently solved with the modal dynamics capabilities within the software, and that's exactly what we're going to do. Essentially, we're going to do two steps. In the first step, we extract the 10 modes, 10 frequencies, and then if you use 5 of them, as the YouTuber that I mentioned does, uh, the mass participation is about 88%, and therefore he decides to go to extract another 5 modes, and that will bring the participation around 90%. Yeah. In step 2, it uses these 10 frequencies uh, uh, and solve it using modal dynamics, and assumes a modal damping of 3% for all the extracted 10 modes. And he gets, of course, this plot, and we're going to replicate this within 3D experience. So let's go ahead here, and we're going to create our beam. So I'll create 2 points here under essential. We're going to create 1 point at this location, and then another point which is let's see, 75 millimeter away. Yeah, so another point along the y-axis, I'll make 75. Okay, let's create a line between these 2 points, one here to there. Okay, and while we're here, let's go and make the material that we want. So under tools, uh, let's see now, create materials. Let's call this thing steel modal dynamics, and it's the beam elements. Okay, and obviously simulation domain is selected, so that's good. Say okay. Uh, all right, right there, right click, apply. I don't need this thing anymore, so I'm going to close that. I'm going to apply it to this. So you can see that it's in the tree. Now we just have to go and input the data. So double clicking on it, and under structural, this is structural, general, density, and the density is taken to be 7,000 890 kilogram per meter cube, which is the density of steel essentially. And then under the material properties, I will select Abacus Multiphysics, mechanical, elasticity, elastic, and that's going to be 200 gigapascals. GPa, and Poisson ratio is 0.3. Yep, and we say OK. All right, that's pretty much it. So we are done here. We're going to go to structural model creation using the standard icon here. Select the defaults. Okay, and now under meshing, I'm going to use beam elements, this thing, and I will use the same size element that this fellow is using, and I believe it is 2 millimeters. Let me check again. 2 millimeter global size. Okay, so let's do that. Mesh size 2 millimeter. That's an overkill, but I will use the same data that the person is using. Okay, so we say okay. Good. And as far as the properties is concerned, we have to go to the properties tab under beam first to create a profile, and it's a circular profile. The radius is based on the data from that tutorial. It's 1 millimeter. Radius is 1 millimeter, right? And this is profile 1. And now we're going to apply beam section to this. And we will use as for profile, we use the beam profile 1, the one that I just created. Material is selected properly, and then that's pretty much it. If you zoom in, you see that actually it's shown right there. Okay, good. Let me actually hide this properties so that I don't see that cylinder there. Very good. So the next thing we want to do is we're going to go to mechanical scenario creation. You can also go to structural scenario creation, but this one is better because there's a stuff here that you cannot do within structural scenario creation. So I go to mechanical scenario creation. Most of my videos until recently was in structural model creation, but I'm switching to the other option. It is going to be structural. Analysis type is structural, and for the finite element model, we select the one that we just created, and we say OK. All right, good. So why don't we clamp this endpoint? So we're going to go to boundary conditions and find the clamp icon. Oh, before I do that, let's go to procedure. We're going to do the frequency step first. Frequency step. 10 modes, and we say OK. All right. And now we go to boundary condition and select the clamp, and we're going to clamp that end. Now, if you can't pick it, uh, either zoom in or zoom in or go and select it from the tree. Okay, that's good. And that's pretty much it. So there's nothing else that needs to be done within this. So let's go to simulation, do a model and scenario check first. Something is missing here. Let's check that. Uh, see what the issue is. Okay, you know that point, that's why you have to be very careful. That clamp that I put was probably at that point, which I don't want to. So let me go ahead to, I wanted the end of the beam actually. So let's go to this restraint, double click on it, say remove this. Now, let's hide that point. That's point number one. Let me hide this. And now this time select the end of this beam. This is something that I don't particularly like, but unfortunately it's maybe happening. So the only thing is that I hit that point and selected that same location, which is the end of the beam. So let's check it out. Hopefully we don't get that message anymore. Yep. Now you got to be careful. This is something that also happens in the CATIA solver, but which is not the uh, Abacus program. It's a different program. And now we're going to do simulation check. Okay. And we're going to make a run. I don't anticipate any problem. We're going to make a run, and we'll have the 10 exacted mode shapes, and modal frequencies. Now, of course, some of them are going to be some of them may be torsional and things like that. In fact, what I'm going to do later on, I'm going to restrict the motion of this beam completely out of plane and from out of plane so that all the modes are bending modes. So let's see now. It did. Uh, Let me simulate it. See, when I do this, some of the axial modes are also going to participate, which I don't want to because this is essentially a bending problem. We let it run, but then we check and see what's going on, and then if necessary, and it will be necessary, we will go and restrict the motion in the direction X so that it just becomes bending. In fact, if you also restrict in direction Y, it becomes strictly bending. There is no axial deformation in it either. Yeah, you can see that it's right here, but and these come in pairs because there's bending about the uh, x-axis and the not the y-axis, about the x-axis and the z-axis, right? Yeah, that's why they become in pairs. But some of these are, particularly these large ones, are probably the axial ones. So what I'm going to do is this. I'm going to close this. Let's go back to scenario, and I will go to boundary conditions, and I will select uh, what is that? Fixed displacement. These all the elements in this line not to move in the direction X. Okay. Now, although it may not be necessary, but it also there's some stuff that we can fix about rotation. Oh, since we want to prevent the axial motion, let me also say X and Y, not let it move in X or the Y direction, so it can only move in the Z direction. Now, these rotations, for example, because of the nature of the problem, we can restrict rotation about Z and rotation about Y, okay? Rotation about Y is already probably fixed. So it can bend about X, but it can rotate about X. So I just uh, fix the unnecessary things. All right, let's go ahead and run it. So we go to simulation. Well, I will not actually do this simulation check and model check, so I just run it. Probably the very first frequency is going to remain the same because that is, I believe, is bending. We can see that later on. So all 10 modes extracted are going to be for me the bending modes. or at least based on the restraints that I put on the beam, the line, it should be only the bending mode. So let's see now. Yep, good. Let's check it out. I'm going to close this. I'm going to look at it directly from the front. So directly from the front, which is right here. Okay, let's look at the first one. There's the first bending mode. There's a second bending mode, third, fourth, etc. So these are all bending mode. Whereas before, I also had the axial and uh, some 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 probably torsional modes associated with it. Okay, good. So we're done here. Now we're going to go to back to the scenario. Back to the scenario. Oh, before I do that, actually, let's go back to this results. Now, I, I want to check the diagnostic viewer here, diagnostic viewer, which obviously there are no issues with it. So let's look at the uh, simulation status. There's a tab right here under diagnostic file right there. And let's see now, if you scroll down, you find the information regarding the mass participation factors and things like that here. So for example, let's see now, these are the frequencies that were extracted. Make this thing bigger. Yeah. And here are the participation factors. So the total mass of this object is probably given somewhere up here. The total mass is right there. Okay. And then you go here and look at uh, the modal participation factor about that would be the x direction. So not the x direction. Let's see. Effective mass modal participation factor, not the x direction, but it's the z component. So it is about the z is right here. Yeah. So these are negligible about these are 0, these are negligible. You can see that. Now this sum, if you look at uh, these are negligible, you can see that. This is modal participation in the z direction, and these are the only ones that contribute. And somewhere there we can probably find out what the actual some of these things is, some of these things as compared with the total mass, and it should be about 80, about 90%. Okay, okay, that's good, very good. So let's close this thing, go back to scenario. All right, for the second step, we're going to do modal dynamics. First step, we should have created frequency, and we did. So we go down here, we go to, what is that, harmonic response? No, modal dynamic step right there. Okay, you click on it. Now, based on the information that I gave you in the slide, the, to the total time is 0.042, 0.042. Time increment, let me see what I use for the time. Now, time increment, keep in mind that this does not do direct integration. Okay, so basically it's calculating the Harman integral. So I will use, I mean, this does not have to be small. Okay, however, I will use the same number that this fellow uses in the Abacus CAE program. So 7.17 e to the minus 5. This is very small. This is small, it's unnecessary, but I'll use the same thing that he does and use all the modes. Now, the damping, we're going to do damping. We're going to do damping in a second. Okay. So there's the damping. Click on it. and we're gonna use global damping of 0. Uh, Everything is gonna get damped by point oh, what is that? 0.5%, right? 0.05. That comes from oh, 3, sorry, 0.03. Yeah. I just want to double check on what this gentleman did. I'm sure it was 0.03. Very good. Okay. Yeah. Global. Oh, this is, sorry, not here. Okay. So this is for proportional damping. Global structural damping. Nope. So fraction. Uh, why don't we go frequency? So for if you want to use for all of them, you can do it one by one. So I'm going to go frequency. What are those numbers that we extracted? So this I have to come back and do that. I mean, obviously you can add, you can just add stuff here, but let me say okay. See now, frequency damping ratio. So I want to put 0.03, 0.03 for all of these columns, but all the frequencies. So I have to. I'll just take the first 3 or 4, but I don't know what they are. So let me say cancel that. Let's go to the results. These are the frequencies. So let me take 4 of them. So 250 hertz, 250 hertz, and then 1563, 4359, and 8494. Okay, so we go back to the scenario. We go back to the scenario. Click on the damping here. You can export this thing with an Excel file too, but I'm not going to do that. So let's see now, 250, 0.03. This one is 1563, 1563, same thing, 0.03. And then 4359.03. And finally, the fourth, I'm using only 4 modes, damping for the 4 modes. 849, I think it was 8494. 84994. And that's going to be 3%, 0.03. Say okay. Good. Now, as far as the data that we want to extract, we need to apply a load here. So we're going to go to boundary load. This is the force. And once again, so that I don't make a mistake here, I'm going to hide that point. I'm going to put it on that vertex. The downward direction minus 100 Newton. Is that right? 100, yes, Newton downward. Okay, but I'm going to use I'm going to create an amplitude and use it. Right now, it says it's default, but I'm going to create an amplitude and use that. Now, the amplitude, see now, on the procedures, it may be the amplitude. I think the amplitude is not here. I believe the amplitude is in model. So let's go back to the model. See if we can find amplitude somewhere. Actually, I'm not sure. So let's go back to the scenario. Maybe the amplitude is here. I thought it was. So let's see now. Under tools, simulate, durability, load, boundary conditions, procedures, setup. Ah, there we are. I'm sorry. It was in the same spot. It was in the scenario, but you have to select the setup tab, and there's the amplitude. You click on it. You say tabular amplitude. So let's put that data in it. The data is basically these points. Okay, 1, 2, 3, 4, and then you go all the way to the end. So we go 0, 0, 0, 0, and then it's 0.001, amplitude of 0.001, amplitude of 1, 0.0015, amplitude of 1, and yeah, and then 0.002, amplitude 0, and then all the way to the last, to the end, which is 0.042, amplitude of 0. But you can also plot this thing, make sure it's right. So we go XY plot is right there. You can see that. Okay, and don't worry about the fact that these two numbers are the same. My number of significant figures is set to 3. That's why it rounded it off for display purposes to this. So smoothing, yeah, we don't need any smoothing. I don't think. Well, you can leave it, but basically those sharp corners, it rounds it off. But I'll leave it. I'll just leave it like this, whatever the default is. Now, the if you look at this load, I don't want to use the default amplitude. I want a tabular amplitude 1. Good. So before I run it, I go to simulation and I select on the output. And for the output, I just select it's going to be history output of this point. Okay. And I want the displacement, and translation of displacement is all I want. It's going to be displacement only up and down, so you can do either um, uh, this or the translation, either one, so it doesn't matter. Or here, use this, and then that's pretty much it. Okay, so we go to first we do a model and scenario check. I don't anticipate any problems, but we'll find out. Then we do a simulation check. It uses those 10 frequencies that we calculated. The first step in modal dynamics is actually finding the modes and natural frequencies. And we did it. And finally, we're going to run it. There are other ways of putting that modal dynamics damping damping ratios. Because what I did, I basically specified the frequencies and then put the damping ratio in it. But there is a way of specifying any frequency in a certain range to be damped by such and such percent. Now, I could not, did not go find that. So to find that, but right here is finished. So this is the frequency step. We already done it. If you go to the modal dynamics step, this is on the form, but this is fine. So we're gonna have to go and do a plot of displacement of that point. So under results, you're in results. Okay, plot right there, plots tab, and let's see now. Here is right here XY platform history. Let's see now. Translation is right there, and magnitude, that's fine, and then apply. Okay, so this is okay. So this is supposed to be that, and the reason it doesn't look like that is that I plotted the amplitude. So I don't want the amplitude, I want the component in direction 3 right there. Now this damping, it looks like it was not taken into consideration. So let's go ahead and find out what's going on here, because there should be damping, and the damping was let me close this, go back to the scenario. I want to check my damping values. Under procedure, there's a damping. Oops, sorry. Damping is right there. Ah, percent damping. So these should be 3. These should be 3, not 0.03. 3, 3, and 3. 3%. And run it again. Bad mistake. Because 0.03%, that's a damping ratio of 0.0003. That's very small. That's why the plot did not show that significant damped oscillation that we got in here. Okay, so let's give it a try. And I'm going to run that thing, by the way, for a time step of less than much smaller than what we had before. The difference will be the fact that the plot will be jagged. So let's see now. Here is our plot. Let me click on it and say apply, and there we are. This is that, and yeah, we can see that the maximum is, this is a millimeter, 100 and something, and over here is also 100 and something. Now I also want, now that we did this, let's go ahead and go to that modal dynamics step right there. Okay, so this tiny one, I'm going to make it 0.001. Okay, and say okay, and run it. That may still be nice and smooth, but we'll find out. Okay, yeah, you can see that. If I mean, essentially, it's the same kind of a behavior, but that basically gives you a jagged. So the curve is still the same thing, but because the number of sample points that they're taking are much smaller, it looks like that. All right, so that takes care of this tutorial. Good luck.